In this video, we are going to see about speed control of switch reluctance motor using Hysteresis Current Controller and myself, Jade Johnson. This is a flow of the project. First, the introduction about the entire motor. Next, the controller which we are using in the project, the Hysteresis Current Controller. Then next is the working of the circuit. Then the subsystems of the circuit. Then we are going to see about the results. First, the introduction. The SRM motor is used as a replacement of other motors in variable speed operation because of its advantage, such as simple construction, wide speed range operation, and there is no winding or magnets on rotor. And it can also be used in hostile environment. The principle of SRM motor is it works on the principle of variable speed reluctance, which means where reluctance means resistance towards magnetic field. The rotor of this motor constantly tries to align through lowest reluctance length. In this project, we have used 6x4 SRM motor. Which means 6 stator poles and 4 rotor poles are there. And there are also 8x6 and 10x8 SRM motor available. Next, the controllers. Fundamentally, there are 3 types of controllers for controlling SRM motor. They are voltage control, current control, and torque control. The controller used in this project is Hysteresis Current Controller, which is the easiest control method to be implemented. But the only disadvantage is there is no limit for switching frequency. But an additional circuitry method can be used to limit the maximum switching frequency. In Hysteresis Current Controller, there are 2 bands, lower and upper band, which can be defined or can be defined by the additional circuitry which I mentioned before. First, when the switch is closed, the current passes when the switch is closed, the current passes through the circuit where it goes from the lower band to the upper band. When it touches the upper band, it will off the switch and decrease the current flow. Again, when it touches the lower band, it will on the switch. It will on the switch again, do it alternatively and generate PWM through which the speed is controlled.
So now we are gonna create an build a circuit for controlling SRM motor using Hysteresis Current Controller. So first, you need to type. You need to get it. You need to have an SRM motor. So for that, you need to type switched reluctance machine and double click on it, and you'll get this parameter blocks and change it to expand 3-phase port, and we are going to use number of pole is 4. So I'm going to change it to P and this as RS, and here change this to specify tabulated flux data, and the current vector will be IPH, and then the angle vector will be theta, and then the current and then flux linkage matrix will be ESI, and click apply and okay. So, and then one more thing is if you want to know these values of P, RS, IPH and TH and PSI, you're going to go to MATLAB and type the variable T, and you'll get the value for the variable. If I want IPH, that is current vector, then I'm going to get the current vectors. So if you want to know all the values for what I'm going to type in this video, you have to come here, you have to come to the MATLAB and type it. So, and then and another thing is we need to get the rotor angle. So for that, I'm just clicking this, enabling it, and click apply and okay. So we have our SRM motor here. We have our SRM motor here. So next we need is an switch. Why we need an switch is because we need to change the stator current from one winding to another. So in order to switch the stator current from one winding to other, we need a switch. So Now I'm going to create a subsystem for that subsystem, and so now double click and remove whatever is inside. And again, I'm going to create a subsystem. In this subsystem, this subsystem I'm going to create for the power electronics. In this project, we are using IGBT. So I'm going to type subsystem. Double click again and remove whatever is inside. And we need an IGBT, right? So for that, I need to type IGBT. So we need idling and switching. So we are going for switching process. So we need an IGBT for switching. So we have an IGBT for switching. So now what we are going to do is we need an input. So we need an input block. This. Yeah. So now I'm going to name this input as G. And we need two connection ports to connect the collector and the emitter to the positive and negative port. So we are gonna, if we need a connection port, so we need a connection port, and then we need another connection. So and rotate this port. So now we can connect this connection port to here, here, and this is going to be the collector. So this is going to be the collector. I'm going to name it as C, and this is going to be the emitter. Yeah. So, so now if I want to connect this input to this IGBT, I need a Simulink PS converter. I need a Simulink PS converter. Why do I need this Simulink PS converter? Is because I'm going to connect. This is from Simscape library. So if I want to send signal from Simulink to Simscape library, I need an Simulink PS converter. So with this will be our IGBT. Okay, so and I need to change this input from left to right and apply and okay. Again, this is also from left to apply and okay. So this will be our power electronics IGBT. So what I'm going to do is I'm going to click it and I'm going to remove this thing. So I'm going to click right click format and then content preview. I'm going to read. So now I'm going to name it as IGBT1. This will be our first IGBT, and we need 6 IGBTs for 6 data windings because we are using we need 6 for 6 data winding. We need 6 IGBTs. So for that, I'm gonna copy it. Now we have 6 IGBTs, and now we need an input variable, right? So for we have to give inputs for this. So for that, I'm gonna need an input. So I'm gonna name it this as yeah. So this will be G. So now I need to connect this G to all the G gate pulses of IGBT. So what I'm gonna do is I'm gonna get a DMARCs. I'm gonna take a DMARC and big and and I'm gonna change this input output ports into B and connect this port to this port and IGBT 1 and 2 for the first input. And the second one for the second IGBT. Third IGBT. Second one to the third and fourth. And then the last one to the fifth and sixth. Okay. With this, we have connected all the gate pulses together. So next thing we're going to do is we need a positive terminal and negative terminal. So what I'm going to do is I'm going to create a connection port here and here another one. Okay. So I'm going to put this as will be like this will be positive and this will be negative. So now we're going to connect all the positive. We're going to connect this positive to all the collectors of the IGBTs. So for that, what I'm going to do is we can move this a little bit and then and move space. So yeah, now I'm gonna connect this all positive to all the collectors of the IGBT, right? So for that, I'm gonna connect it to this one here and this one, and this one. So next thing I'm gonna do is we are gonna connect the IGBT 2, 4, and 6 collector to the circuit. For that we need a diode and rotate it. So why do we need a diode? Is because diode's function is to allow the current to flow in only one direction. So it won't allow in the other direction. So we'll connect this part here, here. And we need 2 more diodes. So 1 and then 2. So now we are going to connect this collector here and then this here. And next we are going to connect all the emitters to the negative port. So for that we need another 3 diodes. So 1 and then 2 and so we need another. It looks right. So we got another 3 diodes. And we connect this part to here. Then we have a little bit right. And connect it here. And we are gonna connect all the terminals here. Yeah. So and then 2 here. Okay, so and then So now all the collectors have been connected to the positive and all the emitters have been connected to the negative. So now we need an output ports for A1 and A2, B1 and B2, C1 and C. So for that we need another 6 connection ports. So I'm gonna copy this, paste it here, copy this and paste it here. Here, here, right. So um, so yeah, we have 6 connection ports. So I'm gonna rotate this, and this, and then connect all the ports to the circuit. Yeah, and uh, and change the name and change the name as this will be A1 and this will be uh, A2 and this will be B1 and this will be B2 and this will be C1 and this will be C2. And now I'm gonna change this from left side to right side. Okay, change it left side to right side. What do you mean by left side to right side is like here everything will be on the left side of the subsystem. So I'm gonna change from left side to the right side of the subsystem. So we can change from left to right. Apply. Okay. I'm going to right. So with this, this will be our switch. That will be this will be our three arm switch. Okay, 3 arm switch. So okay, so what I'm gonna do is I'm gonna remove the preview content preview. So format remove the content preview, and this will be our switch. Okay, this will be our switch. Okay, so next what we need is what do we need? Is a controller for controlling this SRM motor. So for that, what I'm going to do is we need to create another subsystem here and remove all the subsystems. So what we need is an SRM Hysteresis Current Controller, which is already available in the MATLAB Simulink. So what I'm going to type is SRM. As you can see, SRM Hysteresis Current Controller. Click this box, and what I'm going to do is make it big. So we need a reference, a speed input, and then a current input, and an angle input, that is theta, and then theta on and theta off inputs. So these are the inputs we need to give for the SRM, this hysteresis control to work. So first thing we need is how many inputs? 1, 2, 3, 4, 5 inputs we need to give for the hysteresis current control. So first we need input. So we need an input block. So one input block, and 2 paste. Yeah. So this one will be the reference speed. Okay, this one will be the reference speed. And this one will be the actual speed, which we can name it as W. And this one will be the current of ABC. Okay, I name it as IABC. And the last one will be the angle of the rotor. Okay, so we've got four inputs. So now what I'm going to do is I'm going to bring a rate limiter. So rate limiter, what it does is it limits the first derivative of the incoming signal. Okay. So what I'm going to do is I'm going to keep with this rising slew and falling slew as 2000 and then minus 2000. So it's going to maintain between 2000 to minus 2000 RPM. Okay. Can give. So we can apply and then and next will be the rate transition. So what this block is going to do is this block uh, is going to transfer data from the output of a block operating to the at one rate, okay, and then send and to the input of the block operating at a different rate. So from output block operating at one rate, it's going to send to an input and to input in another block which is operating in another rate. Okay. So this is going to maintain the rate of transmission of the signals. So okay, we have a rate limiter and a rate transition. So inside this rate transition, we're gonna keep the sample time as. So if you want to know the value of TSC, you can type it in the MATLAB and you can find the value of TSC and click apply and OK. So we need 4 more rate transistors. So for actual value 1 and for current of IBC 1 for angle 1. Here, so we have 4 rate. We have okay, so now we can connect all this here. And what we are going to do is we are going to find the error value for this two speed. So this is a reference speed which we will give, and this will be the actual speed which you will get from the SRM motor. So what we are going to do is we're going to use a sum block. Sum block, and plus we're gonna add plus minus. So we're gonna minus this 2. So we're gonna find the error value for these two signals. Okay. And what we are going to do is we are going to feed this signal into a PI controller, a discrete PI controller. A discrete PI controller with an anti-bind up. So we are going to use this block. And we are going to change, we are going to give the gate, the P value and I value, the proportional and integral value as KP will be, and then this value will be KI, and this will be 0, and upper limit will be I max, the lower section will be 0, and the sample time will be TSC. And okay. So this value is directly going to go into the hysteresis current controller. So here will be the error. Here is where the error signal is generated and fed into the hysteresis controller, according to which the RPM is maintained in the motor. Okay. So here reset value we're going to give constant block. We need a constant block, and we're going to pin the value into. So next is this will be the current of IABC. We are going to connect this current of IABC to this IABC. Okay, and this angle value theta. So to this theta. Okay. Okay. So we have theta value. So next is theta on and theta off. Theta on and theta off is nothing but when the rotor comes at what angle, when the rotor comes to near the stator, the switch has to on, and after which angle the switch has to close. So we are going to we need a constant block, and another constant block, and we are going to give it as pi by 4, which means at 45 degree, when the rotor is 45 degree to the stator, the switch has to on, and we are going to keep it pi by 2. So when the rotor reaches 90 degree to the stator, it has to off the switch and switch it to the next winding. Okay. So this will be our SRM, that is SRM, hysteresis current control. So this will be our hysteresis current control. Okay. So, and and we need an output, right? We need an output. Before that, we are going to connect it to the unit delay. So it's going to delay the output by unit. So it's going to delay the output by unit. Based on the sample time, it will delay the output. And then we are going to need a gain. So gain block is not gain. It's going to multiply the value of output coming from here. It's going to multiply with the gain value and it's going to send it to the output. So the gain value is so this will be our SRF, hysteresis current control. So it can be out. So this will be our controller. This is the controller, and then we are going to change this output name as G. And another thing is we're going to connect this here and we're going to connect it here. And the other thing is we need to find how much current is flowing from the switch to the motor. So for that, we are going to need a current sensor. So for that, we are going to create a subsystem, another subsystem. So here we are going to use the current sensor. Here, a current sensor for 3-phase. So we're going to click it and we are going to change it to 3-phase. So we have a 3-phase current sensor now. So if you want to know about this block or any block, so you can read the description here or you can click help to find out more about this block. So we are gonna need connection ports. So we're gonna need connection ports. The connection ports, right? And the other side, the connection rotated. I'm gonna change it from right, and then copy it. I'm gonna copy this. More times. Okay, and I need an output block. So now we are going to connect this to the all the so if I want to connect this block to the output block, I cannot connect this block. So I cannot connect the block directly. So what I need is a PS Simulink converter. So from if I want to send a signal from a Simscape library to a Simulink library, I need a PS Simulink. If I want to send a Simulink library to the Simscape, I need a Simulink PS converter. Not PS Simulink converter. I need a Simulink PS converter. Okay. So I'm gonna connect it here. So this will be our current sensor. Okay, this will be a this will be our what? Current sensor. So I can put this output with the top. So I can change it to I IDBC. This will be IDBC. So now I'm going to keep it in between the switch and the sensor. Between the switch and the sensor. Here. Let's connect all the connections first. Oh, I'm sorry, and then I forgot to change the here. Okay, instead of that, we can put 1, 2, and then 3, and it be 4, and then okay. So we have connected our current sensor now. So we can connect the rest of the part. We can connect the rest of the part. We can make it from big ports. So we have a controller, we have our switch, and we have our current sensor, and we have our SRM motor. So what we are going to do is we are going to connect everything together. So, and I need to give an DC supplier. So for that, I need to put DC voltage source. So I'm going to connect it to the positive and negative, and I need a ground. For that, I'm going to connect a ground here. So next thing is I need an rotational damper. A rotational damper because this SRM produces a lot of vibration while spinning. So for that, I'm gonna create I need a rotational damper. So a rotational damper. Um, okay, and I need a mechanical reference. So I need a mechanical rotational reference. So I need a mechanical rotational reference here. And we need a solver configuration. To solve this whole process, we need a solver configuration. Instead of going into modeling and changing the solver configuration, we can keep the solver configuration work. We instead of coming here and changing the solver, we can keep it. We can change it. We can keep a solver configuration. We need a solver configuration for predicted, and we need an inertia block to act as a mechanical you can this block will represent ideal mechanical rotational reduction. Okay, so I'm gonna change this value into so, and then okay. And then I'm gonna change this damping coefficient into D and apply. Okay. So if you want to know these values, as I said before, you can go and check in MATLAB. And next thing I'm gonna do is I'm gonna use local solver. We can change the solver type here, and the sample time I'm gonna keep is it's going to be TS. It's going to be TS. It's going to be TS. And I'm gonna change the non-linear into right and apply and then okay. So now I have inertia and solver configuration part. So what I need is a motion sensor. Why I need a motion sensor is I need to find where the rotor exactly is. So I need to know where the rotor is and how much speed the rotor is spinning. So in order to know the rotor position and the RPM of the motor, I need a motion sensor. So for that, I'm going to write the motion sensor. Motion sensor. So ideal rotation, motion sensor. So I'm going to rotate that. So now I can connect this rotor here, motion sensor R, and then I need another mechanical rotational reference here. I'm gonna put E. So in this motion sensor, the A will represent the angle of the rotor and W is the actual speed which will be fed into the controller. So first, in order to fed this into this block, we need an TS Simulink converter. Then TS Simulink converter. So this one will be the and another one. So I'm gonna connect this angle to into this block, this speed, actual speed into the okay. So now we will to in order to start the motor, we'll know the place where the motor. We'll know which place the rotor is standing. Okay, by this motion sensor. So next, we're gonna connect this current. How much current is flowing? We need to know. So we're gonna send it. We're gonna connect it to the I8DC. So with that, this is our SRM hysteresis current controller. Okay, using hysteresis current controller, we are controlling the SRM motor. So we can okay. Next, we are gonna we will need a constant. We need to give an reference speed, right? So we need a constant bucket. So for this project, for this simulation, I'm just gonna give it as 500. It's 500 RPM. I will paste the name of the reference speed. Okay. So now we have the SRM, hysteresis current controller, using hysteresis current controller. So what I'm gonna do is, so yeah, and I'm gonna change this to degree in black and then here and so so the next thing is what we need to do is we need to display the output, right? We need a graphical representation. So we need to know what is going on. We need to see the output. So what I need to do is I need a scope. I need a scope. So I need a s- I have a scope now. So I have a scope. So what are the things I need to see? I need to see the actual speed. I need to know what is the current of IABC, and I need to know the angle of the rotor. Okay, so for that, I'm going to use go to block. So instead of why I'm using go to block is instead of connecting everything from here, instead of reducing the wires, what I'm going to connect, I'm just going to send the signal directly to the scope. So for that, I'm using a go to block. Connecting this go to block here. And I'm going to take this. So we have good. So we can now see reference speed, actual speed. We can compare the reference and actual speed, and we can see current of IABC, current of ABC, and then the angle. So what I'm going to do is I'm gonna put this tag name as reference speed. Okay, and I'm going to change it to global, and I'm going to apply. Okay. And the next thing, I'm going to put it, this is the actual, right? So I'm going to change it to global. Okay. And the next thing is IABC, right? So I'm going to change it to global and apply and okay. And the last thing is the angle. So now we have the go to block. So from the go to block will send the signal. So how will I receive the signal is using from block. So I'm going to create a subsystem. 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 So in this, I'm going to use from blocks. So from from. Okay. So totally, how many go-to blocks we used? 1, 2, 3, 4. So four go-to blocks. So for that, we need four round blocks. So the first one is going to be the reference speed, and the second one is going to be the actual speed, and the third one is going to be uh, current of IABC. I'm sorry, my mistake. I need to change this to a and angle, right? So I've kept angle. G, you know. And the last one is going to be the angle, right? So the angle. So now I need to compare these two. So for that, I'm going to use a mux block. Mux. So I'm gonna take this one. Okay. So, so I need totally three outputs. So I need to output block 1, 2, and then output 2, and then I need it another one. So then I go and do plot. So now I can get all the output. So now I'm gonna do this. I'm gonna remove this content review. So I have only one output. So I'm gonna change the scope into three inputs. Okay. So I click settings and change it to three inputs. And to view layout and change into three layouts. So after this, we can connect all all the so we can connect all the four switches now. And now I'm gonna give the voltage source. So voltage source will be VDC. Okay, apply. So now I'm gonna give the simulation time as 0.2 seconds. It's going to run for 0.2 seconds. After that, I'm going to show the scope. Okay, let's see. So now I'm clicking the run. It's compiling. So as you can see, the simulation is over. Here. So as you can see, the yellow line is a reference RPM which you have given as 500, and the blue line is the actual RPM. So because I kept 0.2 seconds, it takes more time to catch up to the reference speed. And these are the stator currents of ABC, and this is the rotor angle which will slowly catch up to the speed. So as you can see, this is so if I put a knob here and then try to change the input value as the system is running, it will change the output scope. So this is like this is the SRM motor controlling the speed of SRM motor using hysteresis current controller. So thank you for watching this video.